Why do function approximation helps? You know, it sort of helps. You guys talked about the obvious one, the clear one. The clear one being that if you haven't seen a state before, you can still make a reasonable guess for it based upon generalizing from previous things that have been similar. So you might learn faster. But I think the big thing, and this is the big thing behind all of the modern excitement about deep learning and everything, the big thing is that we are doing approximations, and we are expressing the fact that we are limited. We are only a small brain. We are only a small machine. We only have maybe 1 billion weights. Only 1 billion compared to the enormous numbers in the world of states. And it's not just that we might have never seen this state before. Maybe we have seen it before, but maybe the world has changed. It's a really it's important, even if we've seen the state before, because we're going to see too many states in our life, and we're not going to be able to have weights for them all. It's really expressing our limitations. It's almost like humility to say we only have so many parameters. So anyway, we do have states. The simplest case, generally we have states action pairs, but in the general case we have states coming in, they're going through some box, which is our function approximator. It has parameters W, it has weights. And then from that we get the value for the state given those weights. And finally, the other input we need is the target. We need something to tell us what we should have done. Maybe it could be a person, but of course we're not doing that. We're doing reinforcement learning, so our target is going to come from our experience and our data, and usually from our return or from another prediction if we're bootstrapping. Okay, so that's the big picture. Now I'm going to give you just one slide, the key mathematical ideas. Actually, no. First, I'm going to review sort of what we did last time. We're doing value. So instead of having a tabular value, we're now going to have the approximate value. We're now going to have the approximate value v hat. In all cases, we're trying to approximate the true value of a state, but we're going to approximate with this function approximator. Now notice v hat. The original v pi is not a random variable. This is just a function of state. This is a random variable because it's an estimate that we change over time. This v hat is not a random variable either. It's just a function of two arguments, the state and the parameter vector, the weight vector. So this also is not a random variable. It's just an ordinary lowercase function, produces a single number, a scalar number. And so the weights are a great big vector. In r to the d, we're going to use d for the dimensionality of our vector. So here we have, what, 8. 8 parameters is our vector. And as I reminded you, we always talk about our vectors as if they're column vectors, so they're standing up straight like that. Okay? And given that weight vector, we can now define our function as an inner product between the weight vector and the feature vector. Feature vector looks also standing up. Now often our feature vectors are binary, like this one, zeros and ones, saying, which we can think of, and I'll often use this language, that the feature is present or absent. If it's present, like it's a 1, and if it's absent, it's a 0. But in general, they could be anything. They could be negative feature values. They could be anything, but we have to do the linear form, in the linear form. Okay? So these feature vectors can general any map from the states to, again, real numbers of the same dimension d, real valued vectors. Okay, so, and this inner product, just the weights added up times the features. And, if these are 0 and 1s, then we're really just adding up, then where it's a 0, we're not adding up anything. And when it's a 1, we're adding up the weight. So you could do this just by adding up the weight for this guy, the weight for that guy, or the weight for that guy. If your feature vector was this thing, I think I have that spelled out. Yeah, so here we're picking out where the 1s are. And so we're basically adding up the weights, 0.01, 1.2, 0.5. What do you get? What's that add up to? Are you with me? If we add up the weights where the features are ones, 1.7 and a little bit. Okay, we get 1.71. Okay, that's all we're doing. And so these weights really, if we think about it as a value, and I want you to think about this inner product as approximately the value, then and the feature vector says which features are present, then the weights say, is that a good feature? Is it good that that feature is present, or is it bad? Like if this feature was present, it's not present, but if this feature was present, we'd be subtracting. We'd have a lower value, a much lower value. Whereas this feature, this is a really good, this is the best feature, right? If I get that present, my value would be almost 5 all by its own. Okay, so the weights say how good the features are, and we're adding them up. Very intuitive thing. Okay, so for action values, it's the same thing. Up in the first part of the book, we talked about capital QSA, a random variable, because it's changing over time by a learning process, and it approximates the true value function, which is not a random variable, because it's just a true value that's defined by the problem and the policy. And we're going to now approximate that within an estimate Q hat. Q hat is an ordinary function, but it takes the parameters W. So it can vary as the parameters vary. As the parameters are weights, I may use those terms interchangeably. But don't confuse the parameters. And I say, hey, the parameter W, that's not the same as the parameters like alpha or gamma, which are sort of hyperparameters. Okay, so just keep those straight in your head. And of course, for action values, we'd like to do the same sort of thing, right? And we're going to make them be an inner product with a weight vector and a feature vector. But now, when we're doing action values, the feature vector will depend upon both the state and the action. Okay? Otherwise, it's going to be the same. So we can really treat these cases, they're going to look more similar. We're not going to have two sets of equations anymore. We'll have pretty much one set of equation. And it'll help because I'll be able to talk about the feature vector for the state at time t and the action at time t. If these were capital S at t and capital A at t, I could call that just x of t and cover the two cases uniformly. Okay, so that was a little review. Now let's go further. Okay, we're basically going to always talk about stochastic gradient descent. Stochastic gradient descent. Gradient descent means you're descending the gradient. Gradient just means like the slope, the direction to move into to have things change. Okay, and gradient descent means we're going down, and really just the fact that we have a minus sign is what makes it descent. Later, we're actually going to do some gradient ascent, where we're going to have a plus sign. Okay, it's because when you're talking about prediction, and in much of machine learning, you're talking about reducing errors. Okay, making errors small, so you go downhill in the error surface. Whereas in reinforcement learning, we want to make rewards and values large, so we often go up the hill to maximize our values. Adam.
What's the stochastic part referred to?
What's the stochastic part? Yeah, so the stochastic part, because so far I've really just talked about gradient and descending it. I haven't talked about the descent, the stochastic part. So the stochastic part is because what would it mean not to do a stochastic gradient descent? I think that's the easiest way to explain it. If I said, well, I've got a policy and I've got a value function, it has a weight vector W, and if I try to make that I look at the overall how well I'm doing with those weights. And then if I was for all my experience, all my states, and I tried to get them all correct, I'd have a certain error, and I could descend that error surface. But in stochastic gradient descent, you just take a sample state, and you compute the gradient for that sample, and you make a step down the hill. And that's really what's written here. It says the weight is equal to the new weight is the old weight minus the direction that would reduce. Actually, this gradient is the direction that increases the error, and then we subtract it out. We move in the opposite direction. So this is how changing the weights would affect the error at time t. The squared error, whatever it is, at time t. Okay? Now, you're going to have a different error at every time step. because the state you're in at that time step, you might want to make you remember different states will share weights, and so if you make one right, you're going to make another one worse, and yet you're only seeing the states one step at a time. So you take a random step for that state, and you've got to balance it against the random steps that will take into the other state. So the randomness comes from which state you're running into. Now the randomness also comes because where our targets are going to be stochastic, because our targets are like rewards, which could be stochastic, or returns, which depend on the trajectory. So we really have to balance out different time steps. We're in different places, and compromise all those errors at different times. That makes a stochastic gradient descent. Okay, so now let's specialize this to our case, because that's just a general expression of the idea of stochastic gradient descent in some parameter w, any kind of error. The errors that we are interested in are the errors between some target and the value function approximation. So we'll be looking at the v hat and some state that we're in at time t, and the error that we got from some target, which could be stochastic. Okay, that's what we're going to do. And this for value function approximation. That's what we're all about in this part of the book, value function approximation. First line is for any kind of approximation. And now for value function approximation, we're interested in this error. Okay? Now, I really want to kind of derive the learning rule. We did the learning rule last time. We didn't derive it. But now I'll kind of derive it, because we can use, this looks mysterious, but remember, gradient just means the vector of partial derivatives. Partial derivatives, if you remember your calculus, you can do it. So the derivative of, so we have to say what depends on w. Well, the target might depend on w. This depends on w. It's written there. You can see it. It explicitly does depend on w. Okay? So anyway, this thing in brackets, in square brackets, depends on w, and we have a square of it. So what do you do in calculus when you want the derivative of an expression squared, where the expression depends upon the thing you're trying to differentiate with respect to? Do you remember your calculus? How many of you have taken a calculus courses? How many it was more than 4 years ago? A fair number. So didn't you wonder when you were taking that course if you'd ever have to really use it? Well, I always wondered, and I thought I didn't, and I forgot it all. And then I just took machine learning, and I actually found I had to take some derivatives in order to derive learning rules. It's a really good way sometimes to derive your learning rules. And like you want to find the maximum of something, you find where the gradient is 0. Anyway, so we have to do it here. And we use the most basic calculus thing called the chain rule. You remember the chain rule? No hands came up. Anyway, the chain rule says that thing over there, it's like x squared. It becomes 2x. But then we have to say if x actually is a function. But anyway, we have to do this. Okay? We're going to, with the power of 2 gets moved to the front, and we reduce to power of 1. So we have the same thing to power of 1. So we just have the thing. And then the thing that we just reduced its power, we need its gradient. So we need the gradient of the thing in brackets. Okay? That's just mathematical there. Okay? Now the next, any questions? Chain rule, just calculus. Now we have to make a choice, because it's possible. I want to consider the case where the target does not depend on w. Okay, and if the target, to take the derivative of a sum, it's the derivative of each one of the parts. Okay, so I want to assume this does not depend on w, so its derivative will be 0. So we can just take it out, and we just have the derivative of this thing. Okay, so that gets us our next line. Just this part carries down, and the target disappears, and we just have the gradient with respect to this guy, the gradient of v hat. And the minus sign I pulled out in the front and made it canceled with this minus sign. I got a plus. Is that clear? Anybody other than Adam has a question? What? What? Someone back there. You look at paying attention in the back? Anyone paying attention in the back? See anything wrong? No one's paying attention in the back. But Sina. Where did the 2 go? Yeah, it seems like there's a 2 missing. Okay, so is there a 2? It's a mistake, right? There should be a 2 in there. Magically disappeared. Okay, so is that fair? Or is that just a mistake? Any thoughts?
I guess it's a new step size with double of the last.
It's a new step size, double the last. Okay, so you got it. Well, all I'm doing is I'm saying, well, alpha was always arbitrary. It's just a constant proportionality. So I just sort of cheated by changing my mind about what alpha is. Alpha is now a half of alpha. Anyway, I just absorbed the 2 into alpha because alpha is just an arbitrary constant. Now, some people start this equation. They say gradient descent is the weights are the old weights minus a half alpha. And I always say, well, why you got a random half in there? That's crazy. And then it ends up canceling, okay? But so alpha is arbitrary, and so I've thrown it out. And this is the equation that we looked at the other day. And that's our rule. And the other thing we did was we specialized it to be the linear case. Okay, to be the linear case, the only place that arises is that this gradient, we'll now know what the gradient is because we will have a linear value function approximation. And if you remember, if you take this gradient for the linear case, does anyone remember what it is? What's the gradient of the value function in the linear case?
XT.
It's the feature vector. It's the feature vector. It's x of t. It's x of the state, which we sometimes just call x of t. Okay? And so that's our final algorithm for the linear case. We're going to talk all about the linear case today. I just want to remind you now for the state action value case, for the action values, it's the same thing, except our guess is now an estimated state action pair for that state action pair and our features for the state action pair. Okay? So this one slide has the whole rationale for the algorithms that we use of the 2 kinds. It could be a Monte Carlo algorithm, or it could be a TD algorithm. Now, if it was a Monte Carlo algorithm, all these rules, all these updates would be equalities. These are exactly equal to each other. Now, the one place that what somewhat cheating step that I did was this target. I said, what if the target doesn't depend on the weights? The target doesn't depend on weights, this is all fine. And this is Monte Carlo, doesn't depend on the weights. The target is the actual return. But if you're doing a TD method, then the target actually does depend on your weights. And so we're still going to do exactly this algorithm. We're not going to change the algorithm, but it's no longer an equality. Because in the TD algorithm, we're going to ignore the effect of the weights on the target, and we're just going to do this rule. We're going to ignore the effect of the weights on the target. And so that's why we call it a semi-gradient algorithm. This step is really where we bring in the semi-gradient. It's like there's a gradient. The gradient is the effect of W on both of these things. And we're gonna ignore one of them. We're gonna take the gradient with respect to one, but not the other. So it's part of the gradient, semi-gradient. Okay? That's the difference between Monte Carlo and TD. You might ask, what if you took it into account? And we're going to get all into that later. But the brief story is you don't want to. You don't want to consider the effect of the weights on the target. It's not that it's an approximation and we'd really like to do it. No. For a long time, we all thought it was an approximation. We really wanted to include it, but and it's still a bit controversial. But since you're listening to me, I'm going to tell you we don't want to. Okay? So we're not going to go farther than that actually, because this in 366, but in 609 we will go into it deeper and we will look at that. Okay? Okay, so this then is our algorithm, just to carry it a little bit further for Monte Carlo. Monte Carlo, we input some policy because we're just trying to evaluate some policy v hat that approximates v pi. So we have to provide a differentiable function, and for it could be anything. It could be a neural network, okay? But it has to take in the state representation and produce a scalar that approximate that we will treat as an estimate of v pi. And so our weights are not necessarily the linear weights. They're arbitrary weights. They could really be the weights of a neural network, complicated nonlinear function. Okay, but the weights have to be the size that our parameterization will accept. And so you might start the weights at 0. Anyway, you generate an episode, and when the episode is all done, you go back over the time steps and you change the weight once for each time step to make the estimate for that state that you saw at that time step equal to the return from that time step. Okay? So that's exactly the equation we looked to before, where the return g is taking the place of the target. Okay, so let's carry out with this example and look at a complete world, just an example of function approximation. And I'm going to do the simplest case of it. And I'm going to do the simplest world I could think of. This world is essentially the random walk problem, but it's now, instead of having 5 states, instead of having 19 states, now we're going to have 1,000 states. Thousands, so it's such a big number. Can't possibly imagine having parameters for each one. Well, of course we could. 1,000 is only 1,000, but let's look at what happens if we cannot represent separately every state. Okay, and what I'm going to do is I'm going to take them in groups of 100, and I'm going to say each group of 100 has to be represented with the same state value, estimated value. Okay, we'll do that in a minute, but let me make sure we understand what the problem is. So the problem is we have 1,000 states, and here they are laid out from 1 to 1,000, okay? And you start right in the middle. You start at state 500, okay? Is state 500 right in the middle, by the way? Not quite, right? It's right in the middle would be 500 and a half, okay? Because it's an even number, so there's nothing right in the middle. You notice in the past we always had, 5 states or 19 states. Funny numbers. I guess those are both. Are they both prime? Yeah, they're both prime. But they are odd, so they had a center state. Now we don't have a center state, as we just have a mess of states. And anyway, 500 is pretty close to the middle. And so then, what is the dynamics? Remember, in the past, we would move over one state or move back one state, at random. So instead, now we're going to make a jump. We're going to jump from this state to one of the states on this side, on one of these 100 states, or one of the 100 states on that side. Okay, so S0, the very first state of the episode, is going to be state number 500, and the state 1, the second state of the episode, will either be to the right, 501 to 600, or 400 to 499. Okay? And then we keep jumping, okay? And we pick from that range uniformly, right? Randomly, uniformly, makes a jump, and then we'll make another jump, which will be to its neighbors either way. And this side, we happen to go the other way, right? I've just sorted out, separated the ones going backwards, put them on the bottom. So they're down here, and then you went right again, you went right again, you went left twice, and I didn't want things to all overlap, so I kept going to the right in this made-up example trajectory until finally we go past the end. We could go past either end. And so you're going to go past, you're not going to land exactly on 1,000. You're going to jump and you'll land somewhere here, and so then I just suck you back. That's all considered a terminal state. So if you go past it, on either end you reach the terminal state, you get a +1 or -1. Otherwise you get rewards of 0. And that's my generalization of the random walk task to 1,000 states. Okay, got it? Okay, state aggregation. State aggregation, let me tell you to it in general. In general, you have your state space and you separate them into disjoint sets, disjoint subsets. So we're going to call them groups. And you're going to have one weight, one number for each group. And if you're in, basically if you're in that subset, your estimate is that weight. So if you're in state S, you look up what group is state S in, and your approximate value is the weight of that group. I've just aggregated the states and groups, and they all have to share the same weight, the same estimated value. Okay, so the estimated values will be kind of piecewise constant. Now, this is linear. This is a special case of linear, because if you figure out the gradient, actually, I'm going to do the standard learning rule, and the standard learning rule says construct the error and then look at the gradient. And so you just do it in your head. What's the gradient going to be? What is this gradient with respect to what is the gradient? The gradient is how would the value function be changed as a function of my weights. Okay, so really the value of this state only depends on the weight for that state, because it's going to be that weight. So when you just mathematically, what's the gradient? The gradient is a whole vector of zeros, and there's a 1 for the one weight that corresponds to this state. So it really fits into our general form and falls out of it. So I guess I've actually said something, because this says what the approximation is, and this tells you what's going to happen when you learn. When you learn, you're going to get an error, and then when you do the gradient, you're basically only going to change the one weight. Obviously, which is what the right thing to do is, you fall in some group, and so you get your estimate from that group's weight, and then when you learn, you change that weight, that same weight for that group. And that falls out of the general form. Okay, so that's state aggregation in general. And now we'll do it for our case. So here we're going to have 10 groups. States, 1 through 99, 1 through 100 will be one group. And 101 through 200 will be another group. And so on. And there's going to be 8 groups. And so when we jumped here, this is the same trajectory as before. We were falling, like here we were in a state, and then we moved there. It looks like the same state because we're in the same group. So the value function will be, the value estimate will be the same throughout group 8. Only one number for group 8. So we're going to have 1,000 states approximated the value function over 1,000 states with only 10 numbers. Okay? So it's going to be a crude approximation, right? We just made it hard for ourselves. But this is not unrepresentative. In general, we have many, many, many more states than we have parameters. In general, we can have a more complicated function than a big table of aggregated states. But this is a form of function approximation. And here we've now run the Monte Carlo algorithm that I showed you a slide or two ago. And we've run it on this problem. And I'm showing you two things. Well, this is the results after a large number of episodes with a small learning rate. This is more or less what we converge to. And red and blue. I want you to look at all these things. I guess it sort of draws the eye. The red is the true value function, which we can compute analytically because there's only 1,000 states, so I can run dynamic programming. And as you might guess, that as in the other random walk problems, it's pretty linear. It's pretty linear in the state number. And if I'd given the state number as a feature, then it'd be easy to approximate it. But I didn't give it the state number as a feature. Instead, I told it what group it was in. And it has to estimate it from that. But as I said, it's pretty linear, but it's not completely linear. I don't know. Yes, and the blue is the approximation found by Monte Carlo. Okay, and so the first thing you should see, I guess, is just there's a staircase, And the staircase is because we're doing state aggregation. Each group has to have the same estimated value. All these states have to have the same estimated value. There's no choice about that. That's in the parameterization. All we can do is we can set the height of each group, of each stair. Okay? Good.
Is state aggregation the same thing as doing tabular case with monthly groups as states?
State aggregation is almost like the tabular case. It's almost like it, but it's totally different because in the tabular case, the main thing about the tabular case is you can separately represent each state's value, and you definitely cannot do that in the state aggregation case. You have to share one number for a whole mess of states, and because of that, it really is fundamentally different. It's a special case of function approximation, but it is definitely function approximation. Yeah. There's another question? Yep.
The choice of the number of groups will be based on the number of states and the volume.
Yeah, so this is our first case where we've had to make choices about, and we had to choose the number of groups. And we chose them to be uniformly spread across the space. These are all choices that we've made, and we would choose them. And we don't know. I'm not really proposing state aggregation is a good idea. Actually, I think it's a bad idea. We'll see shortly things that are much better. But even in those things that are much better, you're still going to have to make choices. Like you're going to input your domain knowledge, your human knowledge about what states are similar to which other states. So here we're saying that, well, nearby states are similar. I could have picked groups that took a couple of these and a couple more over there and 100 of them some other place. Your groups can be anything. They just have to be an exhaustive disjoint partition of the state space. And those are all choices that we've made, which would be important in terms of the overall quality of our system. Okay, now, so that's the rough idea, but I'm sure you've noticed a couple things, like these little curves right at the end. It curves a little bit. Curves a little bit over here. And it's not perfect. This doesn't seem the best use of that weight, right? I would get better error, I would think, if I move this guy down a little bit. And things like that. So I want you to think about that and just notice these little details. And now I want to talk about this next thing, the big gray blob here. That is the state distribution. The state distribution says, which states do I care about? And we're absolutely doing what you all suggested the last time we met, that you should care about the states according to how frequently you run into them. Okay? So on this problem, we don't run into the states equally often, right? Can anyone think of one state that we run into most often?
State 500?
State 500. Every episode we visit state 500 because it's the very first state, right? And then this thing, you see this little notch here. I think that's real. I think that's within 100 of state 500, right? So these states, right away, we have like one chance in 200 that they will be the second state. Okay? And so I expect to be visited more often than any other. Well, they're going to be visited fairly often. And so this surface here was computed. I computed it. You can compute it also with dynamic programming. And there's only 1,000 states, so I basically have to do a computation that's like 1,000 squared. And I can compute this surface. And so we learn through this program that we do visit all of the middle states much more often than the edge states. Okay? And it drops off as shown here. This is the state distribution. Okay? And this explains the weirdnesses, the little weirdnesses. So, can you see it? Why? Well, it's not going to explain. Is it? No, it's not going to explain this weirdness. Yeah, I can't explain that weirdness now that I say it to you, because this is the true value. The true value has nothing to do with the approximation. And so the true value, yeah, okay, I guess I have to explain why does the true value do that? Okay, it's too much work for me to do it, so you guys do it. Tell me why the true value doesn't continue linearly up at the edge. It's not the state distribution, because that would only affect the approximation, not affect the true value. The true value is unaffected by how often the states happen. Okay, no one is suggesting it, so I guess I'll have to think of it. Well, you remember how this thing works. This thing works. All through here, it's sort of linear. You could go up or you could go down, and the value. How does dynamic programming? You remember how dynamic programming works? You look at your neighbors. So each state is looking at its neighbors, and it tries to make it like its neighbors. Okay, and so that's why it's linear through most of the space, because if it is linear, everyone's happy. Like everyone, half the time I go up, half the time I go down. When I go up, when I go down, if I go up, if I'm right in the middle, I'm happy because I go up and down half the time. But once you get to the edge, you can go down, and you would go down to some number that's much below you if you take a big jump down. But if you go up, no matter how far you go up, you always get +1. You can't go like to a state 1,050 and get more. The value is still +1. So it's because we sort of level out at the end. You can't go past +1 or past -1. And that means that you end up curving in the true values. That's where these little curves. Okay? Okay, that's that. We explained that to ourselves, at least our approximate satisfaction. But I think we want to explain this part. Why is it, and if you look at it, there is a pattern. Like this guy is too high, and this guy is too high, and this guy maybe is too high. As we get toward into the middle, they're about even. And then as we get out to the right, they're all too low. Maybe a little bit too low. Certainly the last guy is too low. He's not an equal balance from above him and below him. I mean, sure, this guy's tilting up, curving up, but still, there's only a few places where the blue was too low. And there's lots of places where the blue is too high. So, any theories about that? Why didn't this blue guy come down to be a better estimate? Would it be a better estimate?
So because of the state distribution, so the thing affected more.
So we do know that it cares about getting the middle states more. It's more important to get the middle states accurate because they happen more often. So there's going to be more updates with the middle states, and so they're going to be more correct. Okay? And so the guys on the side, we do care about less. So that's clear. But still, we've got to wait for them. And when they do happen, we should get them correct. Okay? So you're close. But it's not just enough to say that we care more about the middle ones. You know, it's like sometimes they have these errors, sometimes they have those errors, and it's like the system is paying more attention to these errors than it is to those errors. So why would it be paying more attention to those errors than these errors?
Because some states on the right are more likely to have the higher.
These states are more likely because the distribution is higher. Yeah, it's exactly what you're saying. So these are given more weight because they happen more often, which we can see. So what's the difference? You know, the height. Look at the height of the distribution here and the height of the distribution here. It's almost twice as high. So those rightmost states are like twice as emphasized as the ones on the left. And that's, and it's similar as we go along, but the difference between the right edge and the left edge becomes less skewed. Like, you know, right in here, there's also, these sides are weighted more than those, but it's a smaller fraction of the overall weight. You know, this would be like 45% and 55% or even less. Rather here it's 50% to 100%. Okay, so that's good. We can this example, I hope it makes sense to y'all. Any questions about this example? Good. Good. The state distribution affects the accuracy. Yeah. Question?
So I'm curious, if you don't update because of distribution, if you let there be just as many updates occurring on the edges,
If there were just as much, if the update distribution was uniform.
right, or if you don't update the states that occur more frequently and only update it so that there's just the same amount of updates, would you get approximately the right value and not be offset?
So the real question is, what do we mean by the right value? And I guess I'll jump ahead. This is my statement. Okay, this is what I propose. This algorithm is doing. This is what I propose is what we care about. So our mean square value error for a weight vector is going to be sum over all the states that could occur, weighted by how often they do occur. Mu of s is how often they do occur. It's the fraction of time. It's a distribution over the states. And then at those states, we look at the difference between the approximate value given the weights and the true value for those states. We square it, we sum it up, weighted by mu. So in general, I'm going to just define the mean square value error for a weight vector as being this quantity, okay? And usually mu will be how often you run into the states in a typical episode, or how often you run into them in the long run in a continuing task with a fraction of the time spent in each state. Okay, so if you I think what you're proposing is, what if mu wasn't there? So we weight everything equally. Okay, but you don't really want that, because some states occur very infrequently. Like some states will never occur. Okay, and you really don't care because you're never going to use them to make a guess. And so you don't really care if you had a bad estimate at a state that never occurred, maybe could not, by laws of physics, could never occur. Okay? You don't care about getting those right. You want to take into account how often. Anyway, you want to be able to express which states you care about, which states you don't. Mu lets you express that, and this measure is good because Monte Carlo methods that do true stochastic gradient descent, they will converge to a local minimum of this objective. Okay, semi-gradient methods like TD will converge near there, but not exactly there. And I think I'll give you that in a minute. And so linear, so they converge to a local minimum. The true statement is they converge to a local minimum of the objective. That means, the objective in general, it's a surface. It's a d-dimensional surface, and it goes up and down, and there may be multiple minima. There'll be a valley here and a valley there, and the only convergence guarantee we have is that you'll be at the bottom of one of the valleys. Okay, you've got a local minima. Now, the nice thing about linear is there's only one minimum. So the global minimum, the local minimum is this one and the same. And but in general, they could have multiple minima, and you're only guaranteed to find a local minimum. Okay. Yeah. Good. Adam.
Is it useful to think of the tabular case as having uniform distribution?
The tabular case, because what happens in the tabular case? What happens in the tabular case? That's a really good question. Asymptotically, I mean. If you have plenty of time to learn, in the tabular case, what will your value estimates do?
True value.
Say again?
They will converge to true value.
They will converge to the true values, okay? And so what will this number be? What will the mean square value error be asymptotically for any tabular method? It will be 0. And so, well, what if I used the uniform weighting here? Would it, what would it then be?
Still 0.
It would still be 0, because all these errors will be 0, and you square them, you're going to get 0, and then no matter how you weight them, you're going to get 0. Okay, so you can see right away that this whole stuff about mu, the distribution of states that we care about, only matters in the case of function approximation. In the tabular case, it doesn't matter a whit. And that's really, because you can get them all right, you don't have to worry about trading off the errors in different ways. Okay? That's a really good question. Okay, so now let's continue with our example. Okay, and I want to continue with the 1,000-state random walk, and now ask you what the TD algorithm will do. TD algorithm, remember, is a semi-gradient algorithm. We're still going to use the same thing, and this is the same. It's a little bit longer because now I'm going to update on each time step, whereas before I finished the whole episode and then went back and did my updates. Now I'm actually going to update on each time step, which is good, and I'm going to, use the TD target, which is the reward plus gamma times the value of the next state. Compare that to the original estimate. Okay, but so it's our usual thing, and this is what it does on this problem, where we can look at the true values and the approximate values. And it's still state aggregation, so we still get a staircase. The staircase doesn't match the true values as well. It tends to be biased up down here and down over there. Doesn't match as well. So if you look at the mean square value error, even weighted by the states as it should be, it's going to be not as good. Nevertheless, the relative values are pretty good. I mean, if you just look at within, because remember this is a TD rule, so it's going to look as it's moving around. Did it go from a state that's better or a state that's worse? I guess the other way. This way would be better. This way would be worse. The relative values are about right, but there's this gap. The absolute difference between the true values is off. It seems like it could be better, and that's what we generally see. We have a larger asymptotic error according to this measure, the mean square value error. And that's kind of a long name, mean square value error. And it's got 4 letters in its acronym. And that's because in this course, well, particularly in 609, in the graduate course, we're going to be talking about several different objective measures, objective functions, several different goals, and we have to give names for each one. That's our first one, the mean square value error. Okay, so it's easy to say. It takes a while to think about if it's okay. Do you remember that we did when we first did TD, chapter 6? We did this A/B example where you saw a little bit of experience, and then you had to decide the values of A and B, and we talked about how they're different from Monte Carlo and TD. Well, this is really that same issue arising, only now it's an asymptotic difference. And asymptotically, they're different. And whether it's better or worse is a more subtle question. Or what we should think about this is a very subtle question. I guess I'm trying to prepare you for my biased answer. Being a fan of TD, as I am, my biased answer is going to be that we still want to do TD. So we have to think about this, but let's recognize this is the fact. The fact is that we're going to have some residual error. We're going to have more error than we would from a Monte Carlo method, asymptotically. So we can now vary. We can do an n-step methods, because remember, n-step says how much bootstrapping we do. Do we bootstrap for one step, like the simplest TD do method, or do we skip 4 steps and then do a TD backup? And so here we're going to vary the distance we look into the future. Okay, and this graph should look familiar to you, because we did something like this on the 19-state random walk. Okay, and those results on the 19-state random walk, I'm going to compare you with them. And I've sort of parametrically set up the problem so that these two cases are similar. So now instead of having 10 groups of 10, we have 20 groups of 50. So there's like 20 groups, 20 pseudo aggregate states as you move across, which is kind of like the 19-state random walk, where you have 19 real states that we jump forward and back. And since we jump forward and back in the 1,000-state random walk, we either jump somewhere, we go forward or back by 100 states. Like I don't mean we jump by 100. We jump somewhere between 1 and 100 states. So an average jump will be 50. So on average, we're jumping 50 forward or 50 backward. And so if I wanted to make it like a 19-state random walk, I've got to make the one step of 50 be like be similar to the one step out of 19. Okay, so if you think about it, if so I move 50 each time, it will be similar if I have 20 groups of 50. Anyway, this is what it seemed to me when I designed it, and it turns out it does. And so this gives me a good. This is the results from chapter 7 on the 19-step random walk, and we can, as we look at it, the qualitatively we're very, very close. Even the absolute values are very close, but we're still like n equals 4 is the best, and it's very similar. So we're seeing the same sort of thing, that we can vary the degree of bootstrapping, and we can compare what happens as we go to Monte Carlo. So we go all the way to Monte Carlo, which would be if we don't do any bootstrapping at all. That's where n is infinity. So remember from chapter 7, this is chapter 7. This is the 19-state random walk. If we did so many steps that 512 steps, a typical episode, a very rare episode, would last that long. And so we're essentially being infinite step TD, which is Monte Carlo. And so we don't do very well. Monte Carlo does bad. According to this measure, this is the average error on the first 10 episodes. Okay? Now the advantage of Monte Carlo is on the asymptotic error. Just like in, it has an asymptotic advantage, but it really is poor if we look at interim performance after the first 10 episodes. First 10 episodes, you really want to do something that's much more towards TD. Even one-step bootstrapping is vastly better than Monte Carlo. We still see the same effect, even with function approximation. We still want to do some TD. Sometimes you only just need to do a little bit of TD, and just get away from Monte Carlo. Dramatically, your performance can increase. So, what I'm trying to tell you is that it's the same, but it's different. It's different because it's function approximation, but it's the same sort of effects we're seeing. We have now an asymptotic difference between the algorithms, but in terms of which algorithms you'd actually like to use, which methods work best, you still want to do some temporal difference learning, some bootstrapping. Okay, good. Let's do just a little bit of theory. Well, do I have time for this? Maybe I don't have time for this. let me save this for the graduate students. We'll just stay just like an extra 5 or 10 minutes and do this slide for the graduate students. Because I want to talk about how you construct the features for linear function approximation. Really key choice, and really all fast learning is going to be linear. And even if we wanted to go to nonlinear things like deep learning, artificial neural networks, the learning is linear in the last layer, and that's the critical layer, determines your representation. So let's think about some ways of thinking about how we can construct the features. The first idea is what we call coarse coding. And coarse coding, it's a lot like state aggregation. So we can think of each one of these circles as a group of states. But unlike function state aggregation, they can overlap. They're not disjoint sets. So when we get a particular state, like state S here, it lies in 3 groups. And so you generalize to all this wide area, and you generalize to various degrees according to how much overlap there is. So if I train you on state S, you will generalize slightly to state S prime, because it has one feature in common, this feature. And the other features are not in common. And these states are closer, and they'll generalize more. And if your state S prime was entirely in this little triangle, you generalize fully to it, as if it was, you generalize fully to it. And now we can choose these receptive fields, these groups. If we choose them smaller, then we will generalize less. Actually, I guess that's the same. But here we're choosing them larger, so we'll get wider generalization. And yet you can still distinguish, even though you're generalizing pretty widely here, you can still distinguish between 2 states because they'll have some features that are not in common. And this is a general idea. Here we can choose them asymmetrically, and you can just see from this picture that this means that if you get a state way up here, it'll still be in common. But if you have a state way out this side, it's not in common. So now we're basically saying, oh, I want to generalize along this dimension, but if you differ along this dimension, even a small difference means you're unrelated. So we can pick the kind of generalization we want by picking these receptive fields of our features. Each circle corresponds to one feature, and that feature would be a 1 if the state falls in that circle, and it's a 0 for if it's outside that circle. So this is a way of thinking about constructing your features. It's called coarse coding, and you have multiple features will apply for any state, and it's really just much better than state aggregation. And here's where I try to illustrate that, and I try to illustrate the difference between having small features or slightly wider features or having really wide features. That's what these 3 columns are. And then as you move up and down, we see time, we see learning. And it's a one-dimensional problem where the desired function is this square. It's like 0 jumps to 1, and then jumps back down to 0. And that's how I'm constructing the targets. This is just supervised learning. I select an input at random along that interval, and I make a guess, and the guess all start out at 0. And then, so when I guessed, if one of these states occurred, and you'd guess 0, and the target would actually be 0, and no learning would happen. And but if by random, if I picked a point somewhere in here, like this point, the target would have been 1, and you'd jump up towards 1. What was my step size? Looks like it was maybe a 10th, maybe a 5th, or something in that range. And over here, it looks like I've chosen a point that got a couple of points, and so I moved almost twice as high, jumped up and jumped up again. Now, for that same data, and it is exactly the same data, if I had wider generalization, see, because this only generalized to a very small region corresponding to how wide the features are. But if I have, let's jump all the way over to really wide, well, let's do this intermediate case. So here we generalize more widely, and instead of having it falling all the way to 0, or not coming up from 0, Here, the whole region comes up. But there's also a bad generalization, because I think these are also high states, even though I haven't been trained on them. And if you really have wide generalization, then you think everything is moved up. And so as you think about it, I don't know, I hope that's clear what's happening. You're generalizing according to instead of circles, we have line segments. We have a one-dimensional problem. And we just have narrow line segments and medium line segments and broad line segments. And there's actually like, there's something like 50 of them across the space. And this is just how wide they are. And if you have very small generalization, you know, you have to learn every little bit. You have to learn these guys go high, and this one you haven't really seen so very much. And so you've got to wait until you sample it, and after 160 examples, you kind of have the shape, but you still have this guy, it's not right. And then you start to get a little ringing phenomenon. But basically, you figure it out, and you can do pretty close to the square pulse. Whereas if you have more generalization, you can more quickly find a good, let's go all the way over to here. You can more quickly get a pretty good approximation. It's up in the middle, down at the edges, but it's harder to figure out. But eventually, after many, many examples, you can get a pretty good approximation to the square. So that's true in all the cases. Asymptotically, they're going to be the same. But the way you generalize, and so the shape of the progression of the learning will depend upon the features. How wide the features are, how much generalization you plan for. Okay, so now I want to tell you about tilecoding. And we may just start that. But tilecoding is a very robust, reliable, it works well. It's not neural networks. And, but it's kind of the state of the art if you want practical, efficient learning. And now I'm going to describe it to you in terms of a two-dimensional space and square, boxy receptive fields. But it is a more general concept, and if you want to use it flexibly to get its full power, you don't want to be stuck thinking about square, boxy tiles, square, boxy receptive fields. But let's do that case, and then we can generalize it. So what's suggested here is, well, we could take the gray part is your state space, and the blue grid you're overlaying on it is a partition of the state space. So it's just like a state aggregation. So each one of the tiles will be a separate receptive field. So this square is what I'm calling a tile, and if you land in the square, you get a weight that's dedicated to you. So if you just did one tiling, a tiling is a tiling of the space into little tiles. If you did one tiling, as in shown in blue, you would have state aggregation. If you then trained on any state, like the state, it would generalize to the whole tile, the whole square rectangular region. But that would just be state aggregation. So instead, we do multiple tiling. So here we have 4 tilings. They're all offset a little bit one from the other. And so now if you get some state, like the white state here, you're in multiple tiles. You're in one tile in each tiling. And so all of those colored tiles would be your representation of that state, and you would generalize from that state to neighboring states, depending upon how many tiles they have in common, which would vary as you get farther away. Okay, that's the idea of tile coding. It is exactly coarse coding made up of exhaustive tilings. Okay, and the biggest, its big claim to fame is really it's sort of designed for modern digital computers. So if you're given some state in some continuous state space, as suggested by the gray region, you can calculate this tile number very quickly. You just do some divisions and some flooring, converting to integers, and you can find that tile number very quickly, and you can do that. So you can find these 4 tiles that are highlighted here. You can find their indices fairly quickly, and that's what you need to do to run very efficient learning and very efficient computation of the value. That's the basic idea of tile coding. Are we going to do a programming assignment that uses tile coding? Okay, so you will have to use this for your value function. Are they going to implement tile coding? They're going to use standard tile coding software. So it's really important, though, that you understand what it is doing, because you're going to have to interpret your results, and you're going to have to correct bugs that might appear. So you have to. So it basically will take in your continuous numbers and produce which are the indices of the tiles. Okay, so I'm going to finish that off. Talk about some of the generalizations. Your tiles don't have to be square, and they don't have to be. They could be any. You can have really funny irregular shapes. I don't know. I've never seen anyone do that, but you could do it. What we could do is to have stripes. Stripes are pretty common, and this is log stripes. Means you might say, oh well, differences down in this part of the space are more important than on that side of the space, and so you have narrower stripes over here and wider stripes over there, which you would do with the standard software just by taking the log of your numbers and then send it to the standard programs, which want to assume that it's all uniform. And if you want to do diagonally, you can take like x minus y and send that in as a number. And you could even, and then we even do hashing. Well, we always do hashing, which is because you're going to have too many tiles. You might have, if you have 4 dimensions and you divide each one into 10, then you like have 10 to the 4th, which is a lot, maybe more than you want. And so you might want to collapse some of the tiles into single tiles. With, and in many cases that has no discernible effect at all. Okay, but to round this off, I wanted to go back to our example of the day, our example being the 1,000-state random walk. What if we did the 1,000-state random walk with tile coding? And, well, I forget what I did exactly. What do we say here? The tiles are 200 states. So I'm just tiling over the interval. The interval is from 1 to 1,000, and I have groups. Each group is 200 states. So it's like take 200 states, and I have 50 tilings. That means like I go from 1 to 200, and then I make it into 5 tiles. That one tiling is then 5 tiles, and then I shift it over. And I go maybe like from 20 to 220, and so on. I get 5 more tiles, and there's a little bit of a round off effect, so there'd be 6 actually. And so then I make 50 tiles, and then I can run and compare state aggregation to tile coding, and we can do much better in terms of we're looking at our error over time, averaged over 30 runs, and we could do much better with tile coding than we can with state aggregation. Adam.
What learning method is this?
What learning method is this? Shoot. I don't know. Look it up in the book.
It's Monte Carlo.
It's Monte Carlo. Okay, that's nice. I wonder what TD would do. That'd be a good project.
Simon 6.
Simon 6? Great. Great. I hope it works well. I love TD. Oh, cross my fingers. Okay, so to wrap up, you could also do this thing with radial-based functions, which are just like tiles, except they're smooth. You might think tiles are bad to have these abrupt things and piecewise constant. Why not have smooth things? Well, you can have smooth things, and this is an example, mountain car, which we'll talk about later. You can do that with smooth ones. It works much the same, just a little bit less efficient. So to conclude, value function approximation is stochastic gradient descent is the name of the game. Enables reinforcement learning to be applied to arbitrarily large state spaces. Most algorithms just carry over. We just take the targets from before, and then we generalize to use the gradient methods. With bootstrapping, you don't get true gradient descent methods, which complicates the analysis. But learning is faster, and you're still guaranteed to converge. For the on-policy case, linear on-policy case, we have convergence guarantees. Of course, we have convergence guarantees for the Monte Carlo case, but we also have for the TD case. And learning can be much faster in the TD case. And if you have a continuous state space, infinite numbers of states, a good strategy is the tilecoding, and for ambitious AI, maybe you want to use artificial neural networks or some generalization of those. Now, so you're all free, but graduate students just stay a little bit longer so we can do that extra theory part. So I just want to do a little bit more thinking about the convergence properties. So you will recognize this as being the TD update. The new weight is the old weight plus step size. And here I've written out, this is the estimated value of the next state minus the estimated value of the current state time t, the one that we're updating. So this is the algorithm. We're just writing out for the linear case, right? And just by pushing things around, you can rewrite this rule as into two parts. And I want you to, this is just a vector. Once we take the expectation, so we're going to take the expectation of the update. This part is going to turn into a vector, which is the expected value of the reward times the feature vector. That'll have an expectation. It'll be a vector. A vector. This part is going to turn into an expectation of x times the change in x transpose. What's that? What's the shape of that object? It's a matrix. Yeah. X times x transpose, or times a vector transpose. So this is a column vector times a row vector. That's a matrix. And that's why, so anyway, so that matrix, x times the change in x transpose, that its expected value, we're going to call the matrix A. R to the D, R times R to the D. So that's, you know, D is a big number. Remember, D is a big number. It's not as big as the number of states, but it's like as big of a number as we can handle to do inner products with it. Okay, so this number, this matrix is too big to handle. Like we could directly estimate this matrix. There's no reason you couldn't. And if you guys read the, you as graduate students, you're reading section 9.7 or 9.8, where one of the sections where we do least squares methods. And least squares methods, they directly estimate this matrix. Because it's pretty big, but I generally think we can't do it, but you know, maybe you could do it. You know, you'd be limited in how big you could make D. And if you directly, so anyway, so this is an important matrix for understanding TD, because you can say, what's the expected change in the weights? Given the current weights, what's the expected next weights? It is the current weights plus alpha, B, where B is basically the expectation of this, and AW, that's the expectation of this other part. So the expected weight change can be written in this way, with these definitions. Any questions? I'm not sure I said that perfectly clearly. Okay, so this gives us our analysis, because now we can say, you know, we want the point when the fixed point is when the expected update is the same as the old W. In other words, when this part is 0. And so when does this part be 0? Well, the alpha doesn't matter. It just matters if this thing is 0. So it's when A minus B minus AW for some fixed point W is 0. That's the fixed point. If it exists, the fixed point will satisfy this relationship. The value of W at which the expected change in W is 0. So in expectation, the weight doesn't change anymore. Okay? That's what we're finding out. And we're going to call that value of W the TD fixed point. WTD. Okay? And so then just by a little bit of transformation, you can figure out what WTD is. And it's the inverse of A times B. Assuming that A has an inverse, and generally speaking, A will have an inverse, or at worst, a pseudo-inverse, so you can still, so it's still valid to talk this way. So this is what TD converges to. You can actually talk about it and manipulate it and find properties of it. And the key property we have is that is this one. So this is the mean square value error of the asymptotic weight vector. That's what we're interested in. We'd like that to be not too big. Okay. Now switch all the way over to this side. Mean square value error of some arbitrary w, but then we're going to minimize it over all w. So this part is the best mean square value error you can get. And that's actually what the Monte Carlo algorithm will converge to asymptotically. It'll find the best weight vector for which this is smallest. Okay? So this quantity from the min on is the numerical error, the mean square value error, the best mean square value error you can get. And then we multiply times this, and TD is less than that. Okay, so this thing we're multiplying by has to be bigger than 1, right? Because this is the very best you can do. There's no way that the weight found by TD can do better than that. Okay? So this number is going to be greater than 1. If you look at it, it has to be greater than 1 because it's 1 over 1 minus gamma. And gamma is a positive number between 0 and 1. So, so this is going to be bigger than 1. And if gamma is close to 1, if gamma is 1 over 1 minus gamma. So when is that? When do we get 1? If gamma was 0. If gamma was 0, then we would be finding the best weight vector. Okay? And what does gamma is equal to 0 mean? No, because lambda is the bootstrapping parameter. This is gamma. This is the discounting parameter. So ignore the long-term consequences. Yeah, that's probably what you meant. Ignore the long-term consequence. So there is no bootstrapping because you make a guess, and then right away, the very next time step, you find out the estimate. And if you think about this whole term disappears because gamma is 0, just comparing the reward to the guess. Okay. And if gamma is long term, like 0.99, this is going to be 100, and we've suffered some expansion. We're just guaranteed that we're within a fairly large expansion of the best mean square value error. Okay, that's our guarantee. Maybe it's a weak one, but at least it's a guarantee. It's a guarantee that we converge somewhere, and it's separately proven that we will converge somewhere. And this separately proved that we will converge, and this is the quantity that we will converge to. That's the TD fixed point. For the linear on-policy case, we will converge, and we will converge to this quantity with this guarantee. Okay, that's done. Questions?
For MC, will converge to exactly the same thing.
Say it again.
For MC, will converge to that minimum exactly.
Monte Carlo will converge to the minimum value. Yeah. Not to this, not to WTD, but to the minimizing value of the weight. But very slowly.
Oh, yeah.
Remember?
That's bad.
So why don't we take the gradient of target and make it full gradient?
Oh, so if you do try to take into account the gradient of the target, you would then be doing gradient descent. But you're not doing gradient descent in the mean square value error. And it will not converge to the weight vector that minimizes the mean square value error. You would be doing gradient descent. But that fundamentally is the reason why. It turns out the thing you'll be doing gradient descent in something, and you'll converge to its minimum, and it won't be very good in general. And that's sort of fully explored in Chapter 11. Chapter 11, of course, is the starred chapter, so we could skip it altogether for this introductory class. But we're going to try to cover Chapter 11. Adam's going to do it on the very next to last class. And we'll try to cover off-policy learning is chapter 11. Off-policy learning is something really exciting to me, because I think to really solve AI, we have to do off-policy learning. But it's also the hardest part. And Andy Bartow doesn't think we should have chapter 11 in the book because it's harder. But I thought it'd be a good mix to have something that was actually hard in the book. And even though it's chapter 11, that doesn't mean it's totally bankrupt, as we would think if you're from the States. Any other questions? Adam?
What if gamma's 1? This thing.
What if gamma's 1? Then the computer goes crazy, smoke comes out, and so you remember. Okay, so I should say, this result is really for the continuing case, not for the episodic case. It'd be a little bit different for the episodic case, but conceptually it's the same. So in the continuing case, gamma can't be 1, right? Because so gamma can't be 1. And I've never seen anyone express in a compact, understandable way what the analogous result is for the episodic case. So I've just shown you the 1.